We will be moving on to section 10.4 and we'll be talking about polar coordinates and polar graphs. So when you have a plane, you can describe every point in a plane with what's called rectangular coordinates. And these are the coordinates that you're familiar with, and they are directions on how to get from the origin to any point. You are familiar with these. You have a x coordinate and a y coordinate, and the x tells you to start at the origin and move in that direction along the x-axis, and then move in the y coordinate direction parallel to the y-axis, and so you end up at a point. And this works really well for a lot of the functions that we have, but for other functions, a different type of coordinate system makes life a little easier, even though it takes a little while to get used to. And so the idea behind polar coordinates is to give a different directions on how to get to a point, how to get to this point right here. And how you get to this point, the way I like to look at it, is you take the x-axis and you rotate it until you're pointing at the point. So you rotate it theta until you're pointing at the point. And then you move along the number line r units until you get to the point. And so then your polar coordinates are always r theta. The first number tells you how far along the number line you move, and it is a directed distance. And the second number tells you how much you rotated the x-axis, right? Here's a nice picture that's in your book. So theta is the directed angle. Directed means it could be both positive and negative. Positive angle is counterclockwise, and a negative angle is clockwise, right? And so then you pick a point. You call that the pole. Your polar axis is going to coincide with the positive x-axis. It's going to go straight right. And when you give the polar coordinates, you're telling how much to rotate this pole and how far to move along it. Now notice this is called a directed distance, right? And that's because we're going to allow in this class for both positive and negative r values, right? And so if this was the x-axis, then and we rotated the x-axis theta, then this would be positive numbers. And then in the opposite direction over here, these would be 1, 2, 3, 4. These would be the negative numbers, -1, -2, -3, -4. And so we're going to allow both positive and negative r values and both positive and negative theta values. So here's a nice picture. It's convenient to draw these concentric circles. So this first circle is a circle of radius 1. Second circle is a circle of radius 2. And third circle is a circle of radius 3, and so on. And so then theta equals pi over 3 is a ray. And so then your ray starts at the origin and goes out this way. And then your point is the intersection of the ray, theta equals pi over 3, with the concentric circle of radius 2. So this is your point right here. So here the polar coordinates are 3 comma negative pi over 6. So that tells you that you are going to rotate your x-axis negative pi over 6, and your point is going to be at the intersection of the circle of radius 3. So it's right here. So this is another way of looking at it. Personally, I prefer to look at it as rotate the x-axis negative pi over 6 and walk 3 units along it. 1, 2, 3. But this concentric circle gives you a nice visual of what's going on as well. This last one is the point 3 comma 11 pi over 6. So what they are not indicating in their graph here is the rotation, right? So 11 pi over 6 means to start here and rotate counterclockwise until 11 pi over 6, giving you a reference angle of pi over 6. Now, you could see that the coordinates are not unique. In rectangular coordinates, there is only one way to describe a point. The point 2, 3, you move over 2 and up 3, there's only one way to describe it. But in polar coordinates, it is not unique, right? So there's more than one way to describe a point. So for example, on this first point, where your radius is 2 and your angle is pi over 3, then we could, instead of rotating only pi over 3, we could have continued to rotate another 2 pi and then the pi over 3, and then walked out 2 units along, and I would still be at the same point. And so then the point 2 comma pi over 3 has the exact same location as the point 2 comma 2 plus 1/3 7 pi over 3. So this negative pi over 6, right? You could have stopped, you could have rotated till you got to over here, leaving you an angle here of pi over 6, which would then make this 5 pi over 6. And then walked out the 3 units along, walked out negative 3 units, right? So there's 1, there's 2, there's 3, but you don't want to walk in the positive direction. You want to walk in the negative direction. So instead of walking in the direction there, you walk in the opposite direction, 1, 2, 3. And so then the coordinates for that point would be a R value of negative 3 and an angle of 5 pi over 6. And so the point being, the polar coordinates are not unique. So, plot the points in polar coordinates. Remember that when I give you points in polar coordinates, it's always r theta. The first number tells you the value of r, how far you walk from the pole. And the second number tells you how much you rotate the x-axis, is the way I like to look at it. So for part A, you're going to rotate the x-axis negative pi over 3. And so you're going to be, the positive x-axis ends up over here. The negative x-axis ends up over here. And since your r value is 2, you're going to walk 2 units in the positive direction. 1, 2. And there you go. There's your point. 2 comma negative pi over 3. For B, there's your plane. Your angle is negative 7 pi over 4. 4 goes into 7, 1 and 3/4. So you're going to go 1 pi and then 3/4. 1, 2, 3. So you will be right there. So your positive x-axis will be over here. Your negative x-axis will be down here. And so you're going to rotate negative 7 pi over 4. That's that right there. And then you're going to walk 1.5 units. So you will be right there, right in the middle. And there you go. For C, you have negative 3 pi over 2. So first you rotate 3 pi over 2. So 3 halves, 1 half, 2 halves, 3 halves. So your positive x-axis will end up right here. Your negative x-axis will end up down here. And because your R value is negative, you walk 3 units in the negative direction. 1, 2, 3. And so you were right here. So this one was 3 halves, comma, negative 7 pi over 4. And this one was negative 3, comma, 3 pi over 2. For D, negative pi over 6. When you rotate negative pi over 6, when you take the x-axis and you rotate it negative pi over 6, then your positive x-axis ends up down here. Your negative x-axis ends up here. And you are walking 5 units in the negative direction. So 1, 2, 3, 4, 5. And there you go. And this will be negative 5, comma, negative pi over 6. For E, you have the angle 4 pi over 3. 4/3 is 1/3 more than 1. 1 is pi. Pi is right there. So then your positive x-axis ends up being over here with a reference angle of 60 degrees. Your negative x-axis ends up being over here. Your R value is positive. And it's positive 2, so you walk 2 units along the positive axes. 1, 2. And so then you are right there. And so then this would be um, 2 comma 4 pi over 3. Okay. And then finally for F, your R value is 0. So no matter how much you rotate, if your R value is 0, and you're going to move 0 along the number line, and so then you'll still be at the origin, at the pole. And so that's an important thing to remember, is that the only way you can get to the pole is if your R value is 0, and every time your R value is 0, the angle does not matter. Your R value is 0. So let me go and fill in the angles. I forgot these angles. For C, the angle was 3 pi over 2. So we rotated 3 pi over 2. For D, it was negative pi over 6. So we rotate the x-axis negative pi over 6. The positive x-axis comes down here. The negative x-axis goes up here. For E, we rotated 4 pi over 3. And there we go. So let's move on. Okay, so we have two different ways of describing a point, either with rectangular coordinates or with polar coordinates. You can see from this picture that you kind of have this triangle, and so then there should be some relationship between them. And so using the Pythagorean theorem or the distance formula, if you're not in quadrant 1, then x squared plus y squared will equal r squared. This relates x, y, and r. So if you know x and y, you can use this formula to find r. And then if you look at this formula, you can use the tangent function, and the tangent of theta is the opposite over the adjacent, y over x. And it really doesn't matter if you're not in quadrant 1, the tangent of the angle is still the y coordinate over the x coordinate. And so then this relates y, x, and theta. And so from these two, we have these results. The polar coordinates r, theta of a point are related to the rectangular coordinates x, y of the point as follows. To go from polar to rectangular, I'm sorry. Now, if you look at this, then if we want to relate x to theta and r, we can use the cosine function. And so then the cosine of theta is x over r, which then gives me that x is equal to r cosine theta. And then using this triangle, we can see that the sine of theta is y over r. And so then we can get that y is equal to r sine theta. So if I know r and theta, I can figure out my x coordinate and my y coordinate using these formulas. And if I know x and y, I can figure out r and theta using these two formulas. And so that's this theorem here. Polar to rectangular, x is r cosine theta, y is equal to r sine theta. So if you know the polar coordinates, your x coordinate is r cosine theta, your y coordinate is r sine theta. Rectangular to polar, so then you can use that the tangent of theta has to equal y over x, but you have to make sure that you're in the right quadrant to figure out your appropriate value of theta. And r squared will equal x squared plus y squared. Okay, so find the rectangular coordinates of the points whose polar coordinates are given. So for A, we know that your r value is -2 and your theta is pi over 4, right? So then a quick sketch, you rotate pi over 4, but your r value is -2, you're down here, right? And so then you want to find the rectangular coordinates. Well, x is equal to r cosine theta, which is -2 times the cosine of pi over 4, which is -2 times square root of 2 over 2, which is -√2. And y is equal to r sine theta, which is -2 times the sine of pi over 4, which is -2 times the square root of 2 over 2, which is -√2. And those polar coordinates match my rough picture there. For B, your angle is negative pi over 4 and your R value is 6. So again, a quick sketch, put that over here. Your angle is negative pi over 4. So you rotate it down and you moved 6 units along the positive x-axis, so you're down here. But then your x is r cosine theta. If you keep writing these things down, you will memorize them whether you want to or not, which is 6 times the cosine of negative pi over 4. Reference angle is pi over 4, 45 degrees. Cosine is square root of 2 over 2. Positive because it's in that quadrant, times 6, so 3 root 2. And then y is equal to r sine theta. Your r is 6 sine of negative pi over 4. The angle of negative pi over 4 puts you in quadrant 4. The sign is negative there. So this is 6 times negative square root of 2 over 2, which is negative 3 root 2. For C, 4 comma 9 pi over 4. And so x is equal to r 4 cosine of theta, 9 pi over 4. So 9 pi over 4, 4 goes into 9 2 complete times, and you have 1 left over. And so then that's coterminal with pi over 4. So the cosine of 9 pi over 4 is square root of 2 over 2, which is 2 root 2. Y is r sine theta, which is 4, and same thing, reference angle is pi over 4. You're in quadrant 1, so it's positive. And so you get 2 root 2. And there you go. So 3, 0. I've run out of room, so I'm going to have to erase some of this up here. Okay, so 3, 0. Remember what this is. This is r, and this is theta. So just a quick picture of this. You rotate 0, and you move out 3 units along. And so then that one there, you could use the formulas, but the rectangular coordinates are 3 over 0 up. And again, you could get there by x is equal to r, 3 cosine theta, cosine of 0 is 1, so you get 3. Y is equal to r sine of 0, but the sine of 0 is 0, so you get 0. And so you get the same coordinates. Okay, so 0, 3 pi. So let's just look at f. And we have 0 comma 3 pi. And 0 comma 3 pi, again, r is 0, so that means you're at the pole. There's absolutely no need to use the formulas. Those become the pole, 0, 0. Now, if you wanted to, you could use the formula x is equal to r times the cosine of 3 pi. Anything times 0 is 0. Y is equal to r, which is 0 times the sine of 3 pi. Anything times 0 is 0. So you get 0, 0. So when your r is 0, you are always at the pole. So in each part, find the polar coordinates satisfying the stated conditions for the point whose rectangular coordinates are negative root 3, comma 1. So again, polar coordinates are not unique, and there's more than one way to describe a point in polar coordinates. First, we'll graph this. Negative root 3, comma 1 is over here in quadrant 2. Negative root 3 comma 1. Okay, so we want your r to be greater than 0 and your theta to be between 0 and 2 pi. And so then, since we know the rectangular coordinates, negative root 3 comma 1, we can figure out r using r squared is equal to x squared plus y squared, which in this case will be 3 plus 1, which is 4, which implies that r is equal to 2. To find your angle, right? So then you're trying to figure out how much do I rotate to get to there. That is your theta. And so then we can use the fact that the tangent to theta is y over x, which is negative the square root of, 1 over square root of 3. Negative 1 over the square root of 3. You should recognize that as possibly being a nice ratio from the 30, 60, 90 triangle. So this was 60 degrees, this was 30 degrees, this was 1, this was 2, this is the square root of 3. Tangent is opposite over the adjacent. So then the tangent of 30 degrees is 1 over the square root of 3. So that gives us the reference angle, pi over 6. And since from here all the way to here is a pi, and we're 1/6 away from pi, so this implies theta is equal to 5 pi over 6. We're 1/6 away from 1. So the polar coordinates are r, theta. So for part B, we want a negative r and an angle between 0 and 2 pi. So negative r means then that we don't want our positive x-axis to end up here. We want it to end up down here. We already know what this angle is, pi over 6. So that means this one over here is pi over 6. And so then to get from here to here, we need to rotate 11 pi over 6, 1/6 away from 1. And so then my angle is going to be 11 pi over 6, but we want to walk in the opposite direction so that we end up over here in quadrant 2. And so then that is going to be negative 2. For C, we want our R value to be positive. So we already know what the R value needs to be. It needs to be 2. But we want our angle to be between negative 2 pi and 0. So that means we're going to go clockwise. And we're going to go 1/6 more than 1. So then 7/6. But we want it clockwise. So we want negative 7 pi over 6. And then for D, we want our R value to be negative and our angle to be between negative pi and pi. And so again, we want our R value to be negative, so it has to be negative 2. And you can see that if we drop down negative pi over 6, my positive x-axis will be here. We'll shoot up in the opposite direction and end up there. So -2 comma negative pi over 6. And there we go. So we're going to sketch some polar curves. Might be useful to make a table of values for some of these. Sketch the graph whose polar equation is r equals 5. Theta r. So if theta is 0, my r value is 5, because that's what it says, r is 5. If theta is pi over 2, my r value is 5. If theta is pi, my r value is 5. If theta is 3 pi over 2, my r value is 5. If theta is 2 pi, my r value is 5. So no matter what my angle is, I walk out 5 units along that. So just plotting those 4 points real quick. That's 5, 5. Those are the quadrant angles. -5, -5. And so then I would get, when theta is 0, I get that point. When theta is pi over 2, I get that point. When theta is 3 pi over 2, I get that point. And when theta is 3 pi over 2 there, I get that point. And so no matter how much I rotate, I always walk out 5. And so then what you should see is that what this is a circle. And that's one of the nice things about polar coordinates. The equation of a circle is very simple. R equals 5, right? Now, what you're also going to need to be able to do is write these equations in rectangular form, and there's no set way of doing that. You just have to play with it. But we do know that r squared is equal to x squared plus y squared. So when you have the equation r equals 5, if you square both sides, you get r squared is equal to 25, and that allows you then to replace the r squared with x squared plus y squared equals 25. And now you can recognize that from your work in pre-calculus as being the equation of a circle of radius 5, which is what we have. Theta is equal to 3 pi over 4, right? So again, what we saw in the last example was when your r value is always a number, that made sense, then your graph was a circle. Now, your theta is always a number. So if r is 0, your theta is 3 pi over 4. If r is 1, your theta is 3 pi over 4. If r is 2, your theta is 3 pi over 4. If r is -1, your theta is 3 pi over 4. And if r is -2, your theta is 3 pi over 4. So graphing this in the xy plane, you can see that 3 pi over 4, 0 is the pole. At 3 pi over 4, 1, you rotated 3 pi over 4 and you move 1 unit out. 3 pi over 4, 2 is over here. And if you go 3 pi over 4 and go in the opposite direction, you get -1. And then if you go in the opposite direction, and you get -2. And what you have is a line. And it should make sense that the polar equation theta is a constant, whatever that constant be, is going to be a line, right? And we can see that by taking the tangent of both sides. If theta is equal to 3 pi over 4, then the tangent of theta is equal to the tangent of 3 pi over 4. And so then the tangent of 3 pi over 4 is -1. And tangent of theta, if you want to put it back the rectangular equations, is y over x. And so you can see then that y is equal to -x. That is the equation of this line. in general, anytime you have theta equals a constant, then your equation will be y equals the tangent of the constant times x. And so then the tangent of the constant then becomes the slope. So the tangent of that constant angle is the slope of your line. And we're going to use that in a little bit. Sketch the graph whose equation is r equals theta. So you have on your graphing calculators, you can change in the mode. You can hit mode, which is over here next to the second function. And you can scroll down and put it in polar and then hit enter. And then when you go to y equals, it gives you an opportunity to input your functions as a function of theta. And so here, sketch the graph whose equation is r equals theta, when theta is bigger than or equal to 0. So again, theta, r. If you rotate 0, your r value is 0. If you rotate pi over 2, your r value is pi over 2. If you rotate pi, your r value is pi. If you rotate 3 pi over 2, your r value is 3 pi over 2. And if you rotate 2 pi, your r value is 2 pi. And so what's going on there is when at 0, you're at the pole. When you rotate to pi over 2, you're at pi over 2. And when you rotate to pi, your r value is pi, so you're way out here. And then 3 pi over 2, and then 2 pi. And what you're doing is you connect those, and you just keep going around, and you get a spiral. And it's just going to spiral. Not very easy to graph that curve using rectangular equations. We're not even going to go over how to change that to rectangular equations. That's not very easy to do. Okay. Sketch the graph whose equation is r equals the cosine of theta. We can start with the table. Theta, r. When theta is 0, cosine of 0 is 1. Use the quadrant angles. When theta is pi over 2, the cosine is 0. When theta is pi, you get negative 1. When theta is 3 pi over 2, the cosine of 3 pi over 2 is back to 0. And at 2 pi, the cosine is back to 1. And then it's just going to go around and around and around. And so the graph should be the same. So to help us graph the polar curve, we're going to graph up here the on the r theta axis the rectangular equation, right? So when 0, we get 1. At pi over 2, we get 0. At pi, we get negative 1. At 3 pi over 2, we get back to 0. And at 2 pi, we're back to 1. So this is the graph of the cosine function. And we're going to use that to help make our polar curve. This is a polar curve that's graphed in the xy plane. When my angle is 0, my r value is 1, so we start out here. Now, as my angle rotates from 0 to pi over 2, you can see that your r value starts at a maximum of 1 and comes down to r value of 0. So then right here, then the curve starts here, and as you rotate, you're going to connect to this point right here, and your R value as you rotate uh, more and more, your R value gets smaller and smaller until it gets to 0. Now once we get past pi over 2, all of our R values are negative. So from negative pi over, from pi over 2 to 3 pi over 2, all our R values are negative. All right, so that means that when we're going from pi over 2 to pi, so my R values, instead of being over here, my points, instead of being over here in quadrant 2, because my angle is in quadrant 2, my points will actually be in quadrant 4, because they have negative R values. So again, what is going on there is from we're at pi, we have R value of -1. So instead of being over here, we're actually over here, and the whole time my R value starts at 0 and then climbs to an R value of 1. Okay. Now, once we get from once we get to 3 pi over 2, we're back to 0. And then from 3 pi over 2 to 2 pi, we're positive again. Oh, I'm sorry. So this point that this last point right here corresponded to the coordinates of pi, comma, -1. And now we need to get to from pi, 3 pi over 2, from pi to 3 pi over 2 for this part. Let me go ahead and change that color. Purple. This part right here. Instead of being over here in quadrant 3, because my R values are still all negative, I'm actually in quadrant 1. And so then there at 3 pi over 2, I'm at 0. And then I come back down. So let me start this again. Let me start this again. Something's not. Okay. So let's make this red. As my angle varies from 0 to pi over 2, you can see on over here that your R values will vary from 1 to 0. So at 0, I'm at 1. And then at pi over 2, I'm at 0. And you can see from the curve that my R value is just getting smaller as my angle increases. So as my angle increases, my graph does that. Okay, so that's from 0 to pi over 2. Now from pi over 2 to pi, I'm starting at an r value of 0, so I'm at this point right here, and let's put that in blue. I'm at this point right here, and my r value decreases from an r value of 0 to an r value of -1. That's in blue. But my angles are from pi over 2 to pi. They're in this quadrant. But instead of my points being in that quadrant, because my r value is negative, I'm actually down here. And that's going to happen from pi over 2 to pi. When right here at this pi -1, that's this point right here. Because my angle is pi, so I should be over here, but because my r value is negative, I go in the opposite direction. Now, from 3 pi over 2, from pi to 3 pi over 2, from pi to 3 pi over 2 is the purple. It's still a negative r value. So pi to 3 pi over 2, I should be in this quadrant. But I'm not. Because my r values are negative. So at pi, I'm right here. And then when I get to 3 pi over 2, I'm back at an r value of 0, so I'm tracing it out again in that direction. And then finally, once I get past 3 pi over 2, now I'm in this quadrant. And let's make that black. And my points are in that quadrant because my r values are all positive. As you can see right here, all these r values are positive. And so then I trace out the bottom half again. So in going from 0 to 2 pi, I actually went around this thing twice. But the question is, what shape is this graph? I have it looking like an ellipse, but what shape does it have? If we multiply both sides of this equation by x, I'm sorry, by r, then I get r squared is equal to r cosine theta. That allows me to make my substitutions. For r squared, I can put x squared plus y squared. And for r cosine theta, I can put x. Subtract the x from both sides, and I will get x squared minus x plus y squared equals 0. If I add 1/4 to both sides, then I will get x minus 1/2 squared plus y squared equals 1/4. And you can see that what this really is a circle of radius 1/2 centered at 1/2 0. And so that is what it is, circle of radius 1/2. Sketch the graph whose equation is r equals sine 2 theta. Okay, so again, where you should begin with a problem like this is first graphing the rectangular curve, right? And so to graph the rectangular curve, theta r, from trigonometry, you should know that the way you make these graphs is by making sure that your angle hits all the quadrant angles, right? And so that means that that because of the 2, that means that you're not going to necessarily put in just the quadrant angles. You have to think ahead. So to get 0, you're going to put in 0. And the sine of 0 is 0, so you get 0. You start at the pole. But then to get pi over 2, you actually have to put in pi over 4. Because then 2 times pi over 4 becomes pi over 2, and the sine of pi over 2 is 1. To get pi, you need to put in pi over 2. And when you put in pi over 2, you get 0. I'm sorry, you get 2 pi. You get pi, and the sine of pi is 0. And then to get 3 pi over 2, you actually have to put in 3 pi over 4. And you're just going to go up by a quarter. And when you put in 3 pi over 4 times 2, you get 3 pi over 2. Sine of 3 pi over 2 is negative 1. And then to get, then you put in pi, you just go up by a quarter. And the sine of 2 pi is 0. And you're just going to keep going up by a quarter. So what you've just done is you've gone through one complete cycle. Your period is only pi, but you haven't gone all the way around yet because you've only gone to pi. So in your trigonometry class, we would stop, but you really should keep going. But what we can do is we can make the graph r theta. We're going to go up by a quarter, 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, 8 quarters, and that will be 2 pi. At 0, we're at 0. At pi over 4, we're at 1. At 2 pi over 4, we're back at 0. At 3 pi over 4, we're at negative 1. At pi, we're back at 0, and then we're just going to keep going. And so what this guarantees me is that I go all the way around and that I make sure I get the entire graph. Okay. And so now let's graph our curve. So let's pick up this part. So 0, 0, we're at the pole. As my angle changes from 0 to pi over 4, my R value changes from an R value of 0 to an R value of 1. So pi over 4 is right there, and we're going to get to an R value of 1. And you can see by following this that as my angle gets bigger, my R value gets bigger, and so then that tells you this graph looks like that. When you're going from pi over 4 to pi over 2, then your R value starts to get smaller, and that pi over 2, you're back at the pole. So then you're there. Okay. Now once you get past pi over 2, so you're over here in this quadrant, your R values are all now negative. You can see that right here in this part of the graph, your R values are negative. And so that means that instead of being in quadrant 2, you're going to be actually over here in quadrant 4. So your R values are negative. You're starting out at an R value of 0, and at 3 pi over 4, that's that angle right there, you're an R value of negative 1, so you're actually down here. And so then your graph connects like that. Now once you get past the 3 pi over 4 to pi, your R values are still negative. That's this part of the curve right here. But your R values are still negative, so instead of being down here, you're actually reflected over here. And so there you go. And you can see that you're not done yet. So you're going to have to do this again. Once you get past pi, so that's pi over 2, that's 3 pi over 4, that's pi. Now we're past pi over here to 5 pi over 4. Your R values are positive. So at 5 pi over 4, you're back at a high of 1. And now your R values are positive, so you're in that quadrant. Once you get past 5 pi over 4 to 6 pi over 4 or 3 pi over 2, your R values are positive, so you're in this quadrant right here, but you're supposed to be connecting back to the pole because your R value goes back to 0. Okay. Okay, so now we're past the 3 pi over 2, and we're supposed to be over here in this quadrant, 3 pi over 2, 6 pi over 4, 7 pi over 4. But in 7 pi over 4, you are from 3 pi over 2 to 7 pi over 4, you are not in this quadrant. You have a negative R value, so you're supposed to be in this quadrant, going from an R value of 0 to an R value of -1, making you 1 unit away from the origin. And then finally, once you get this last piece right here, all of those R values are still negative. You're going from an R value of -1 back to an R value of 0, meaning you go back to the pole. So you connect down there. And there you go. You get a 4-petal rose. So you could put that into your graphing calculator and hit graph. I can give you something like this so that you can't do that. So that you have to understand what I was doing with the R's and the thetas. And so then I expect you to be able to do that. A graph is given in rectangular theta R coordinate system. Sketch the corresponding graph in polar coordinates. Okay. So put the axes in black. X, Y. You can see that when theta is 0, my R value is 2. That tells me I'm 2 units away from the origin. So that is where I start. This part tells me that my R values are positive and coming down to 0. So at an angle of 30 degrees, pi over 6, my R value is 0. So 30 degrees, you can draw a 30-degree angle there. And then your R value goes from an R value of 2 to an R value of 0. Okay. And then this part of the graph looks like that's going from, you're going up by pi over 6. So this would be 2 pi over 6, 3 pi over 6, or pi over 2. So 2 pi over 6 is pi over 3. That's 60 degrees. And so then when you go from an R value of 60 degrees, I'm sorry, from an angle of 30 degrees to an angle of 60 degrees, your R value is always negative, and it goes from an R value R value of 0 down to an R value of -2. So you're going to be 2 units away from the origin when you get to 60 degrees. So so then you're going to be down here, 2 units away. And that whole time, instead of being in quadrant 1, you're actually in quadrant 3. You're connecting like this. Okay. Now, once you get from 60 degrees to 90 degrees, you're still negative. You're going from a minimum of -2 to 0 at pi over 2. So then instead of being here, you're going to be negative, so you're going to be down here. Okay. And now that's 3 pi over 6, so that means this is 4 pi over 6, 2 pi over 3. So 2 pi over 3 is 120 degrees, I believe. And so then from from 90 degrees to 120 degrees, your R values are positive. And so then they're in the right quadrant, starting at 0, going to 2 again. That takes care of this part. Now, once you get from 4 pi over 6 to 5 pi over 6, that's 150 degrees. And so then 150 degrees is over here. Your R values go, that's these R values right here. They go from a max of 2 back down to 0, so you're back at the pole. And then from 5 pi over 6 to pi, these angles right here, your R value is negative, and so then you are not in that quadrant, you're over here, and you're closing up the loop because at pi, you're exactly at -2, so you're connecting over here to this point. And so that last loop was what was going on here. Some curves that are useful to know. When you see R equals a constant, it's going to be a circle of radius A centered at the origin, right? If you see R equals 2A times the cosine of theta, that's going to be a circle of radius A centered on the x-axis. If instead of the cosine you see the sine, then the graph of the polar equation below is a circle of radius A centered on the y-axis. You have some rose curves. So if you mess with the inside and throw an n in front of it, you get petals. What's interesting is that if n is even, you get the same number of petals. I'm sorry, you get twice the number of petals. And if it's odd, then you get the same number of petals, whatever n is. Some nice shapes there that you can play with your graphing calculator. You have R equals A plus or minus B times the cosine of theta. If the ratio of A to B is less than 1, then you have a Lima cone with inner loop. If the ratio of A to B is exactly equal to 1, you get a cardioid. If the ratio of A to B is between 1 and 2, you get a dimpled limacon. And if the ratio of A to B is bigger than 2, you get a convex limacon. Not going to do too much with that. Let's move on to identify the curve by transforming the given polar equations into rectangular coordinates. So for A, there's no set way on how to do this. You just have to have the equations that relate the polar and the rectangular in your head and see what gets sparked. If we multiply both sides by the cosine of theta, you will get R cosine of theta is equal to the cosine times the secant is 1, so is equal to 5. So you get x equals 5. So that turns out to be a vertical line. For B, we know that if we have R sine theta, we could put a y. So if we just multiply both sides out of that equation by R, we will get R squared is equal to 2R sine theta. For R squared, we can put x squared plus y squared. For R sine theta, we can put y. And you can see that that's going to be a circle, as I showed you earlier. For C, again, we can multiply both sides by R. I know to do that so that I can use my R cosine theta, replace it with x, my R sine theta, replace it with y. But I get R squared is equal to 4R cosine theta plus 4R sine theta. And now R squared is x squared plus y squared. And R cosine theta is x, R sine theta is y. And you can complete the squares and write that as a circle in standard form. For D, we can multiply both sides by r as we've seen before. That'll give us r squared, or actually, r is equal to 1 over the cosine of theta, sine of theta over the cosine of theta. And then if we multiply both sides by the cosine squared, we will get r cosine squared of theta is equal to the sine of theta. And you could see then that this needs an r and this needs an r, so we can multiply both sides by r, and we'll get r squared cosine squared of theta is equal to r sine of theta. And so then r cosine theta is x, so that's x squared, and r sine of theta, r times the sine of theta is y. And so that is just a parabola. Y equals x squared. Express the given equations in polar coordinates, right? So we have y equals -3. And if we want polar coordinates, we have our formulas. That x is equal to x is equal to r cosine theta, y is equal to r sine theta, so we can just replace the y with r sine theta equals -3. And then we can divide both sides by the sine of theta, so r is equal to -3 times the cosecant of theta. And there we go. For b, x squared plus y squared, we know that's r squared. And we can square root both sides. No need for the plus or minus here. It's still going to be a circle. R equals the square root of 5. Keep that simple. X squared plus y squared plus 4x equals 0. For the x squared, we have x squared plus y squared plus 4x equals 0. For the x squared plus y squared, we can put r squared. For the 4x, we can put 4 cosine, x is r cosine theta. And equals 0. And there we go. Okay, and so then for D, x squared, r squared, cosine squared theta, x squared plus y squared, r squared, equals y squared, r squared, sine squared theta. Except for the pole, the r squareds go away, leaving you with r squared is equal to the tangent of theta squared. If we square root and we ignore the plus minus, r is the tangent of theta. Let's do some calculus with this. For the curve defined by the parametric equations x equals f of t, and y equals g of t. The derivative is defined by the parametric equations, right? So this is, I think, the easiest way of doing this. Y prime is dy dx, which is dy dt divided by dx dt. Recall that the rectangular coordinates xy for the point whose polar coordinates are r theta are given by the formulas x equals r cosine theta and y equals r sine theta. So then what you can see then is that if you have your r as a function of theta, then you can parameterize your curve and use parametric equations instead of a polar equation using these two formulas, that x is equal to r times the cosine of theta, y is equal to r times the sine of theta. Once you have a parametrization, then you can use the derivative that we've already found. If r is a function of theta, then we get the parametric equations. X of theta is equal to f of theta times the cosine of theta. Y of theta is equal to f of theta times the sine of theta. All right? So we'll write the polar curve using parametric equations. Right? So easy enough. X is equal to r cosine theta, but r is 2 plus 3 cosine theta. And then times the cosine of theta, because x is equal to r cosine theta. This is r cosine theta. Y is equal to r, 2 plus 3 cosine theta, sine theta. And there we go. So now that we know how to parameterize a polar curve, we can then find slopes of tangent lines. No need to use anything other than what you already know. So find the slope of the tangent line to the polar curve for the given value of theta. Slope of the tangent line, dy dx, right? But y is equal to r, 1 plus cosine theta. Sorry, y is equal to r sine theta, which is the sine of theta plus the sine of theta cosine theta. And x is equal to r, 1 plus the cosine of theta, times the cosine of theta, which is equal to the cosine of theta plus the cosine squared of theta. So then dy dx is just dy d theta divided by dx d theta. No need to memorize a whole other formula. Dy d theta is the derivative of the sine is the cosine. This next one is a product, so you have to use the product rule. Derivative of the sine is the cosine. Cosine squared of theta plus, leave the sine alone, take the derivative of the second one, cosine, but the derivative of the cosine is the negative sign, so that's why I put this minus here, and then you get sine squared theta. And then in the denominator, dx d theta, derivative of the cosine is the negative sign, plus composition, bring down the exponent, take one away from the exponent, times the derivative of the inside. And the derivative of the inside is the negative sine of theta. So this becomes minus sine of theta. Okay, so then dy dx evaluated at theta equals pi over 2 is equal to cosine of pi over 2 is 0. So everywhere you see a cosine, you get 0. Sine of pi over 2 is 1. So you get negative 1. And then sine of pi over 2 is negative 1. And everywhere you see a cosine, you get 0. So the derivative evaluated at pi over 2 is 1. So again, x is equal to r cosine theta, a secant 2 theta cosine theta. Be careful, the secant and the cosine do not multiply together to make 1 unless they have the same angle. These do not. One's 2 theta, the other one's theta. Y is equal to r, a secant of 2 theta sine theta. So then dy dx is equal to dy d theta divided by dx d theta. And dy d theta, the derivative of the secant is the secant tangent. Secant theta, tangent theta. Leave the sign alone. Ooh, but that was the secant of 2 theta. So that should be 2 theta, and then you should have a 2. Leave the sign alone. Plus, take the derivative of the sine, which is the cosine of theta, and leave the secant of 2 theta alone. Dx d theta, and the derivative of the secant we've already done is a2 secant 2 theta tangent 2 theta cosine theta minus a secant 2 theta, derivative of the sine is the derivative of the cosine is the negative sign. Both terms have an a. Sorry, all the terms have an a. All the terms have a secant of 2 theta. And so then this formula cleans up to tangent 2 theta sine theta plus cosine theta divided by 2 tangent 2 theta cosine theta minus sine theta. Okay. So then dy dx evaluated at 30 degrees, tangent of 60 degrees, 60 degrees, 30 degrees, 1, 2, square root of 3. So tangent of 60 degrees, root 3. Sine of 30 degrees, 1/2. Plus cosine of 30 degrees, root 3 over 2. So then 2 root 3 times root 3 cosine of 30 degrees, root 3 over 2, and then minus 1/2. These go away, and you get root 3 plus root 3 over 2, all divided by, these go away, 3 minus 1/2. If you multiply top and bottom by 2, you get 2 root 3 plus 1 root 3, 3 root 3, and 6 minus 1 is 5. And there we go. Find the polar coordinates of all points at which the polar curve has a horizontal or vertical tangent line. So again, x is equal to r, a sine theta, cosine theta. Y is equal to r sine theta. And then dy dx is equal to dy d theta divided by dx d theta. And so horizontal is going to be where dy d theta is 0 and dx d theta is not. Vertical is going to be where dx d theta is 0 and dy d theta is not. So dy d theta is equal to 2a sine theta cosine theta. Dx d theta is going to be a cosine squared of theta minus a sine squared of theta. And so horizontal we want um, 2a sine of theta cosine of theta to equal 0. So that means this will happen wherever either the sine of theta or the cosine of theta is 0, and that happens at all the quadrant angles. So theta is equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi. But at 2 pi, you're going to get the same point as at 0. So you're going to get the pole. So no need for that. And then vertical, you're going to want a cosine squared of theta to equal a sine squared of theta, which means then that the tangent squared of theta is equal to 1, which means that the tangent of theta is equal to plus or minus 1. And so then your theta is equal to either pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Notice that there is nowhere where both of them are 0, so this is good. You need to make sure that both of them are not 0. And so then the problem asks for the polar coordinates. Well, then I ran out of room here, so you could then just use your angles in your formula and get the polar coordinates. Not a big deal. I'll let you do that. So if r equals f of theta, then y of theta then the parametric equations for y of theta are f of theta times the sine of theta, and the parametric equations for x of theta are f of theta cosine theta. So then dy d theta, we could use the product rule and take f prime of theta times the sine of theta plus f of theta times the cosine of theta. Dx d theta, same thing. F prime of theta cosine of theta plus f of theta, minus sine of theta. And so then dy dx is f of theta cosine of theta. I'm just switching the order to match what's in the result. F prime of theta sine of theta all divided by f prime of theta cosine of theta. I'm sorry, I wanted to match the result. Just switch the order. And that looks like a complicated formula. And so that's why I did not give you that formula. You can just parameterize the specific equation that you have and then use the results from before. But something nice does happen here. So this is theorem 10.11, slope in polar form. If f is differentiable function of theta, then the slope of the tangent line to the graph r equals f of theta at the point r theta is, and here's the formula that we just derived, f of theta cosine theta plus f prime of theta sine theta, and then minus f prime of theta, minus f of theta sine of theta plus f prime of theta cosine theta. Okay, now if you happen to be at the pole, then the only way you are at the pole is if your r value is 0. And so then if your r value is 0, all of this goes away. And then you can cancel out the f prime of theta. And so then dy dx will equal the sine of theta over the cosine of theta, which is the tangent of theta. So your slope of your tangent line is the tangent of theta. And then it turns out that you get this if f of theta equals 0 and f prime of alpha, if f of alpha equals 0 and f prime of alpha does not equal 0, then the line theta equals alpha is tangent at the pole of the graph r equals f of theta. So if you're going through your pole, then the slope of the tangent line is the tangent of alpha, and so then the equation in polar form turns out to be theta equals alpha. So again, your slope m is equal to the tangent of alpha. And so then your equation is y equals the tangent of alpha times x. And if you divide both sides by x, you get y over x equals the tangent of alpha But y over x is the tangent of theta, your input variable. And over here you have the tangent of alpha. And so then you can see that this will imply that theta equals alpha is a possible equation. It's just because the graph is just a line, theta is equal to alpha is the line. Okay, so sketch the polar curve and find the equations of the tangent lines to the curve at the pole. Theta r. Again, start at 0, sine of 0 is 0. Right? But then we go to pi over 4 because we're trying to hit pi over 2. But because we're multiplying it by 2, we have to put in pi over 4. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. And then we go up by pi over 4, which so then we'll go to pi over 2. 2 times pi over 2 is pi. Sine of pi is 0. And then we'll go to 3 pi over 4. And when we go to 3 pi over 4, then 2 times 3 pi over 4 will be 3 pi over 2. Sine of 3 pi over 2 will be negative 1. Okay, then we go up to pi. Sine of 2 pi is 0. You're back to where you began. And it's going to continue. This pattern is going to continue. You're back at 0, so then you'll go to 1. Then you'll go to 0. Then you'll go to negative 1. And then you'll go back to 0. And this is 5 pi over 4. 6 pi over 4, 3 pi over 2. And then 7 pi over 4. And then finally 8 pi over 4, which is 4 pi. Sorry, 8 pi over 4, which is 2 pi. Not 8 pi, 2 pi. So at 0, we're at 0, we're right here. And from 0 to pi over 4 is 45 degrees. My R value goes from 0 to 1. And then from pi over 4 to pi over 2, we're positive. And we're still there. But now from pi over 2 to 3 pi over 4, all my angles will be negative. So instead of being here, they're actually here. And so then instead of being up here, they will actually be down here. And then from 3 pi over 4 to pi, they're still all negative. So instead of being over here in this quadrant, they're over here. And then once we get past pi, my R values are back to being positive. So it starts 0, go to 1. And then past 5 pi over 4, so my points are actually in this quadrant. Past 5 pi over 4, they're still positive, so we're over here, coming back to the pole. But now, once I get past 3 pi over 2, instead of being in this quadrant, they're going to be over here. Right? So then we started an R value of 0, go to an R value of negative 1. And then we come back here. And then at 2 pi, we're back at 0. So sketch the curve and find the polar equations of the tangent lines. So theta equals 0. You're going through the pole at 0. So theta equals 0 is 1. Right? And so then at pi over 2, you're also going through the pole. So theta equals pi over 2. And then at pi, theta equals pi. And then at 3 pi over 2, so theta equals 3 pi over 2. And then at 2 pi. Let's see if I can do this well. Your tangent line is horizontal right here, and it's vertical right here. And then theta equals pi turns out to be the same line as theta equals 0. Theta equals 3 pi over 2 turns out to be the same line as theta equals pi over 2. And so those lines are tangent to your curve at the pole. There is your homework.